Then we move on to the keynote. So it's my pleasure to introduce Professor Christopher Carothers from Rensselaer Polytechnic Institute in Troy, tells me, New York. He is also the director of the Center for Computing Innovations. So I've been working with Chris for the last, year and a half, maybe, on OMNeT related stuff. Chris is an absolute internationally recognized expert in the field of parallel distributed event simulation. However, he has his own framework called ROS, so we had to do a little bit of convincing, to get him to touch OMNeT, but eventually he did, and he really helped us a lot in improving the parallel simulation capabilities of OMNeT. So, Chris, please.
Thank you. Thank you, Cyril, for both inviting me here and the wonderful introduction. I want to start by introducing our team. So I have Elsa Gonzarowski and Justin. They're two of my PhD students, as well as computer scientists. And then we work with actually Phil Heidelberger, who's just down south of us. So we're only about 2 hours north of Manhattan in lovely Troy, New York. So Phil works at the T.J. Watson Research Center, and of course, Herman, Cyril, and Bogdan, you know from being here in Zurich. All right, so so sort of the agenda for my talk is as follows. I'll talk about some of the motivation and goals for it, the background of how we came to this, and then I'll give an overview of, because part of this work is, of course, getting OMNeT to run well on the IBM supercomputer. This is third generation in the Blue Gene family called the Blue Gene Q. I'll then give sort of an overview of parallel discrete event simulation for those of you that might not be so familiar with that piece of OMNeT or how that really works. And then I'll talk about a new algorithm. It's not so new, but it would be new to the OMNeT community, called YANS. Stands for yet another windowing network simulation. Its implementation. Then I'll talk about sort of how we had to port it to a Blue Gene Q system. Blue Gene Q is by far not your standard Linux box, so there's certain issues there, some performance results, and then plans for the future. All right, so again, first off, backing up, this work was funded by the Department of Energy's Design Forward program. Now, the first thing you're saying to yourself, Department of Energy and supercomputing might not immediately make sense to you, but it turns out, at least in the United States, the Department of Energy has probably been the biggest driver of high-performance computing and supercomputing really within the US. The National Science Foundation is still there, and there's other agencies, but really, for the last few years, the DOE has been driving it. And in fact, the Design Forward program is really geared toward the design. The DOE works with vendors in particular, not just IBM, but really all the vendors, in terms of designing these next generation systems. And so one of the activities that we got involved with IBM on is really part of the network design piece. It's just one component of a much, much larger program. Again, the Department of Energy's interest in supercomputing was largely driven from one of its key mandates in nuclear test ban. Its mandate is really to certify the nuclear stockpile. And again, because of the nuclear test ban, they can't really do live testing anymore, so they need to do simulations, which drives the need for these large supercomputing systems. And so then vendors like IBM end up working with the Department of Energy to really help design these systems, and that's what our program is around. So Cyril, I gather, has been working with their network simulator piece that's built on top of OMNeT called Venus. And this is really a significant investment and part of IBM. It's been around for the last 5 years that they've been working on. And again, it's really been leveraging OMNeT's large capabilities in terms of building these really highly detailed network simulators. In fact, I would say one could make the argument that these are almost hardware specifications of what will ultimately go into these networks. And so they're leveraging all the rich classes that you can have here, the simulation kernel, the random number generation, topology discovery, the net language. Wow. Venus really loves the net language. It's really using it to its full capability. However, we really, I think early on in talking with Phil Heidelberger about this, there was a observation that the sequential simulation execution times for the needs of these next generation networks, so we're talking about models with orders of, well, at the time we thought it could have been 100,000 nodes in such a supercomputing system. That has since been reduced. But essentially, the execution time of these models could take days, possibly even weeks. And so then there was a real interest and need to extend OMNeT's current capability with Venus to allow scalable parallel event simulation on the Blue Gene Q. So in fact, what we're really doing is coming full circle here. We're leveraging the existing investment in supercomputing technology and hardware to help design the future systems that everybody will hopefully enjoy. Again, our goal for this project was really a 50 to 100x speed up using the Blue Gene Q. All right, so let's talk a little bit about, so what is this IBM Blue Gene Q? It's sort of the third generation system. First off, it's composed of racks. So we talk about a rack of Blue Gene Q. A single rack will have 1024 nodes, where each node has 16 cores. So then a rack has 16 3D4 cores up to, and then it's actually, it has the ability to do threads on it or multiple tasks. So that you can actually, it's 4-way hyper-threaded or simultaneously threaded. So you could have up to 64K threads or MPI tasks, which stand for the message passing interface, per rack. And then there's a range of systems. You could have 1 rack, 2 rack. In fact, the largest system that was ever put together was at Lawrence Livermore, and at one point it was 120 racks. That was the Sequoia system out there for a very brief time. It actually backed down to 96 racks. In terms of the processor itself on each one of these nodes, it's a A2 processor, so it's sort of like, I guess, a stripped down power of some sort. 1.6 gigahertz, 16 cores. What was interesting in previous generations of supercomputer systems, and this is what would bite a lot of us in parallel simulation, was this notion of OS jitter. Turns out that as you scale out your parallel computing tasks and doing synchronization on it, if things didn't arrive or need to be synchronized at about the same time, you would see some degree of jitter. And a lot of this jitter was generated actually by the operating system. So this is really solved by having a dedicated core, the 17th core, that does that for you. Additionally, to improve overall yield, there's a sort of hidden magic 18th core that's sort of disabled if all the other cores are operational. In terms of floating point performance, it's around 200 gigaflops plus a reasonable amount of memory. At least it was a lot more in 2012. Today, folks might like to have more per node, 16 gigabytes per node. The memory bandwidth was actually was fairly well balanced against the actual network capability, so it's close to around 43 gigabytes a second. I think the peak was around 23 or something that anybody's really gotten. Very nice amount of cache, and what's really amazing about the cache is its bandwidth. So in fact, we've actually seen very super linear speed up results because of this on strong scaling tests, where you're actually taking a fixed size problem and slicing it up smaller and smaller and smaller as you scale up. So we've seen that behavior. It's very power efficient, even by today's standards, something like 2 gigaflops per watt of power. And then the other piece is the amazing network, and this is really what enables us to run all sorts of parallel applications at scale. In particular, OMNeT, my simulator, is a 5D torus. It has roughly 2 gigabytes of link for the communications. It also has specialized things for handling the collective operations. So these are operations where every task is involved in doing this calculation or synchronization at the same time. And so we'll actually be leveraging that in our reporting of this. So this is what we have available at Rensselaer. We have a 5-rack Blue Gene Q system. And so we feel very fortunate, and IBM is very much our strategic partner with this system. We obtained an NSF grant along with that strategic partnership to put this together. In addition to our 5-rack system, we have a couple of different clusters at our site, Intel clusters that we can leverage, as well as we have about 2 petabytes of disk, leveraging the IBM now. We're actually in the middle of a storage upgrade to IBM's Elastic Storage System. And finally, everything, and this is sort of unique to our center, so all of our compute resources are connected to really a common InfiniBand core, at least from the storage. Obviously, the Blue Gene Q has its own 5D torus, but the clusters and everything all share a common storage system, and everything is interconnected by our core. So this is really where all the calculations for this project were done at our site. What made our system sort of balanced was the fact that we were actually really I/O rich. So I didn't talk too much about the I/O nodes, but I/O is actually done separately. So there's a set of cabinets and a collection of nodes inside there, and we're actually about 4x more dense with these I/O nodes than most blue G&Q systems. One of the interesting side effects of that is it allows us to run a rich range of jobs in this 5D torus setup. In particular, we can run one node debug jobs all the way up to basically full machine size jobs in a number of different configurations. All right, so now bringing into OMNeT. So let's start back. So the basic parallel capability that OMNeT provides today was this notion of what was called the null message algorithm or null message protocol, NMP. The other name it can go by is Chandy Mizra O'Brien. Essentially, it's a protocol that goes all the way back to the late 70s, in fact. What's interesting is I think it was a protocol ahead of its time in the sense of the networking hardware really hadn't caught up to what was needed to power such an algorithm, especially for discrete event simulation. And so this gives you sort of a loop level view of what's going on. Again, the idea, and this is really the hard part with any discrete event simulator, is this need or demand to ensure that what is done in parallel, so the total event ordering that you saw you have in parallel is exactly what you would get if you were to run your model sequentially. And it's really sort of somewhat of a hard thing to do. And that's the constraint of parallel discrete event simulation. So essentially you have this notion of a bunch of FIFOs off each of your simulation entities or logical processes, as we've called them. So they go by different names. And there's at least one message in each of your FIFOs, and then you have to remove the smallest one from the FIFO, process that event. And then here's the kicker where the null messages come in. You send a null message along each of your FIFOs that you have, and then this indicates that lower bound on future events sent to a logical process or a C-simple module or a module. And essentially, with this new lower bound, and I'll talk a little bit more about that, plus a transit time, this really becomes the promise time, if you will, that you're not going to send any other events smaller than that time, and then that's how the synchronization algorithm works. What's sort of interesting, so there's some variations you can do on this. Essentially, you can have LPs or your C modules possibly request null messages if a FIFO becomes empty. So then you can actually reduce. In fact, this was a lot of research around reducing null messages. One of the side effects is it can be delayed. So essentially, that sort of minimum time along each of your FIFOs I was talking about is really that notion of look ahead, if you've not seen this. And this becomes really critical for really all of parallel discrete event simulations. If I were to use an airport example, we can have promise times, if you will, among airports. So if you have an airport simulation, and I'll show another animated example of this. So essentially, we could say if you were in ORD at some simulation time, and there's a maximum transit time between airports of, say, 3 hours, and you're at time 5 hours, then the next message by ORD will be at time 8. So this is sort of that's really an example of in your model where look ahead happens, right? Now in our network models, we leverage what's called link look ahead, right? So essentially, anytime you have a link, there's some delay along that link, and you can sort of guarantee that your next message will be of at least that timestamp in the future plus any link delay. You can also have internal, within the, say, a C-simple module we call a logical process, look ahead as well in there. So essentially, again, this look ahead is really inherent in the model. So whatever you're modeling, those physical timestamp increments sort of define or become what your look ahead is going to be. So the interesting side effect is you could have a great parallel simulation, and then your manager comes knocking at your door and says, we need this new feature in your model, and it could reduce your look ahead by a significant amount, and then that could radically change your parallel performance, and I'll show an example of that. So one of the problems that you could end up with is this notion called time creep. So here we've got 3 logical processes. Again, I'm using airports as an example, which I've been flying lately, so this is very, very reasonable for me. Fortunately, I didn't have many delays. So as again, the problem here is we're going to see that if your look ahead is small, but there's not a lot of activity going on in your network, then that can create some artificial synchronization that isn't completely necessary. We call this sort of the time creep problem. So here we see I send null messages, a timestamp of 5.5 that I go to SFO, and I keep on going, and it keeps going around, and I haven't yet processed any messages because there's nothing in the FIFOs allowing me to go forward yet, because I've got a message of 9 at JFK, 7 at ORD, 10 over at SFO. Finally, we can process the one at 7 after several rounds, and so we end up with this problem of 5 null messages to process a single event. And this is sort of what the time creep problem is. And it can happen in models where sort of you have this behavior where you've got this small, delay, link delay that is sort of constraining the entire model, but in many cases you don't have that. So this is one of the issues with null message. So again, we're saying many null messages here if the minimum flight time is small. So this sort of gives you a picture. This is some older results, but it sort of shows you if you have very large amounts of look ahead. So again, this is a plot of what's called the inverse look ahead. ILR is the inverse look ahead ratio, which is look ahead divided by your average timestamp increment. Overall, if your look ahead is large, you get really good performance. If it's small, so if you have essentially a very large timestamp increment for the amount of look ahead, then you'll get relatively not as good performance as you'd like to see. So this is really where conservative algorithms make or break. And so this is when you're building your model, you sort of have to begin to think about possibly how you can extract more look ahead out of it. All right, so now let's get to yawns, and I'll talk a little bit more about why we're using it. But essentially, we wanted to avoid sending too many null messages. And the nice property about yawns is it's going to exploit the really fast collective operations that are available on the IBM's supercomputers. But it's not just available there, it's available probably on many other systems as well. So again, this is a web-newing type protocol where essentially we start off by pulling all the events off the network, and then we're going to sort of put them into a priority queue, sort them, and then we're going to say pull out the smallest event, and if it's greater than or equal to what's called our global virtual time, which is a lower bound timestamp among all unprocessed events in the system, then we're going to go ahead and compute a new global virtual time. And I'll talk more about how we do that. Then we'll go ahead and break if we're into the simulation time, but otherwise we'll go ahead and start processing events, pulling everything out of the priority queue, subject to this sort of window of the events that we can process are generally less than GVT plus that look ahead. And then once we've exhausted that, we'll go back to the top and do this all over again. So this is the basic yawns protocol. And again, it lives by us being able to calculate this global virtual time. I'll talk a little bit more about that. We actually, originally when we were going to do this work, we were thinking, well, we can take our existing ROS simulator that we have and just sort of stuff it in there. And we thought, well, this will really work well because we had already implemented yawns in there, so we just need to replace the event processing loop of OMNeT and we could probably make this work. It turns out OMNeT has some object ownership rules that require how things are processed and who can have access to what when. And so and ROS is written in pure C, so it knows nothing about the object ownership. It's just bulk memory access. So it didn't have any of that in there. So we couldn't directly do that. So we had to back off. But we knew we could pull elements of the yawns implementation into OMNeT. And I'll talk a little bit more about why we're choosing yawns as we go forward. The other nice feature we took on is we still held with the NET language, we can actually switch between the different parallel protocols. So you can switch between either null message or yawns within your config files. All right, so here's sort of why we were picking yawns, because we knew that it would really perform well. If you have a model with relatively large look ahead, we knew that it would scale well, and this was taken on 16,000 cores of Blue Gene L at the time. Blue Gene Q, the performance isn't going to differ that much. And this was in our ROS simulation. And again, that's comparing against what's called optimistic or time warp, which is sort of it tends to achieve some of the best performance, although there's some cases where conservative can still beat it. So we felt good that, if we had good look ahead overall, or a good inverse look ahead ratio, we would get good performance. But we were concerned that if it wasn't good, that we could end up down at the other end of this curve. But we felt that this would be a good starting point for this piece of work. And this just sort of shows you what the capabilities are. In terms of, on this graph, we're showing the event rate. So we're talking about systems that are capable of doing billions of events per second. All right, so I want to come back and revisit this. So I mentioned this global virtual time calculation which we're using. Another way to look at it, or if you've heard of it, it's also called lower bound timestamp, or LBTS. So that's also, if you read papers about conservative synchronization algorithms, they'll use LBTS when they talk about it. In the optimistic world, we'll tend to use GVT. The reality is they're basically the same thing. They just refer to it slightly differently. What's interesting is, so in optimistic, because you're speculative, we use GVT as a mechanism for reclaiming memory in the speculative execution. What we can use GVT here for, and the conservative, is repurpose it, of course, for the Jan's algorithm to allow us to advance time, right? All right. So the first part of this is, with GVT, we want to, it's actually a sort of a synchronous algorithm, in the sense where there are asynchronous algorithms, but we want to leverage the collective operations of the blue gene. And again, these collective operations allow all these MPI tasks to be synchronized. So you could be doing a barrier, for example, or a all reduced type operation. That can happen across a whole machine in tens of microseconds, or order 10 or less, actually. And for a machine, I'm talking a machine the size of Sequoia, 96 racks or something like that. So again, with this synchronous algorithm, we're going to count messages, right, the sends and receives. And once we've received all of our messages, we're then going to do an all reduce on the sum of everything we've counted of sent minus receive. And essentially it has to get to 0. So every rank, every MPI rank in this parallel simulation has to know that there's no outstanding messages in the system. There's nothing stuck in the network, right? So then once we've done that, each core, or each MPI rank, will compute its own local virtual time, which is essentially what's the smallest unprocessed event in the system. So it's really the event probably in your priority queue for the most part, right? So they'll take that number, that timestamp, and then go in and do an all reduce, minimizing across all the local virtual times across every MPI rank. Again, this is another collective operation. So this takes around order 10 microseconds. This takes 10 microseconds. So it's very, very fast, even at scale. And so once we have this calculation, we can then use it in the Jan's algorithm. Once we've computed GVT, we can advance GVT plus the look ahead, and then essentially the algorithm keeps on going and starts processing events again. All right. So now, how did we? So the challenge then is how do we sort of put Jan's into the API of OMNeT? In particular, it has the parsim part. If you've looked in the source code of OMNeT, has a pretty well-defined API for supporting these things. It actually already has not only the null message algorithm or null message protocol, it has an idealized or ideal synchronization protocol. And so essentially to write a new algorithm, you just need to overload and rewrite these existing routines, and then voila, you could have your new parallel synchronization algorithm for the most part. And the ones in bold I'll actually cover, which are really start run, the end run, process outgoing messages, receiving, and get next event. And these sort of make sense. In fact, the interesting thing in our running joke in this work is the two hardest things with parallel simulation are starting up the simulation and then getting it to terminate, right? Everything in between becomes a little easier once you get it going. So we'll talk about that. But again, the first part we have to do the class constructor destructor. There's some set context stuff that we're not using because we're not really doing sort of process-oriented simulation. We're doing purely event-driven. So we didn't have to worry too much about that. Also, we don't have to worry about rescheduling events. All right. So the first part is how do we do the start run, or what is it going to do? One of the interesting things is there's a notion of the partitioning information that happens, and computing then a correct look-ahead calculation across all those partitions. So you can imagine you've got this network with all these gates in there, the gate objects or channels, and essentially there's an algorithm already in there, or a piece of code that does this for you, and so we have to do that part as well. Now, one of the things we want to do is we want to set, well, what's the sort of, in the Jan's algorithm, you'll use a notion of max simulation time as part of the synchronization protocol. We'll use that in cases where maybe there's no more events to be processed. So maybe a rank says, I'm going to just, I don't have anything to process, so my LVT is max time, right? And so that's one option. Except one of the problems is the OMNeT simulation time is sort of an integer-based representation of time. It has its own sort of fixed point format. One of the problems we had is the max time notion, when we tried to use it, gave us sort of a negative number. We think there's something with the way the representation of the bits are being messed with on the blue gene in particular that caused it not to work. Want to look at that. Maybe I'll get some time while I'm here to actually hack on this. So we just said, well, what's the largest simulation time we'll ever think about running in Venus? Venus, a long simulation might be 100 milliseconds. So we said 10 seconds is probably a good number for that for now. But again, we want to fix that and make that a better representation of time. So this is where start run works. In the case of end run, this is still part of a work in progress. It deals with exceptions partially, but it's going to compute one last global virtual time if needed. Essentially, if one rank decides to do a GVT, all ranks had better be there because these collective operations deadlock effectively. If somebody tries to exit or leave, you leave everybody else hanging with this. And so we need to make sure that everybody participates in every single global virtual time calculation. We also clean up the look-ahead calculation, so that's what we're doing there with in-run. Now, process outgoing messages, we didn't have to change too much here from what was in the Jan's algorithm, in the sense that it currently is going to use the blocking MPI operations to send all their messages to push them out, and we actually pack them into a single memory. So one of the interesting assumptions OMNeT makes is that your C messages need not be contiguously allocated in memory. They can be sort of, have very complex data structures in them. So essentially, there's software to pack up the message. Now this flexibility does come with an overhead, but it packs it into a single block of memory. Interesting enough, records its the module ID and the gate ID information, says this is a C message, and then goes ahead and sends it out. We also increment our send counter, and that, as I showed, was used by our GVT algorithm. So this is essentially what our process outgoing message does. On the receiver side, it essentially does the unpacking part, and we increment any our counter there for the receive part using the GVT as well there. All right. So now I'll show you real code. I guess no OMNeT talk would be complete without showing real code. This was actually the heart of the algorithm called get next event. So get next event is actually used at the top of the scheduler loop as part of selecting the context. So get next event actually is part of saying, well, do you have anything to process? And so this was really where normally in the Jan's algorithm, we would have just had all this would have been part embedded in the scheduler loop. So we pushed a lot of our Jan's functionality that I described earlier into this method itself. So essentially, we stay inside get next event until we sort of exit under certain conditions. The first part says, well, we're going to keep going through this for a batch number of times, and then essentially we have a way of controlling the frequency with which GVT is executed in here. There's actually 2 steps to doing the GVT part. Part 1 just sort of sets some flags up, and step 2 really does that main part that I alluded to earlier about with the 2 collective operations. But these were pretty much taken almost verbatim out of our raw simulator. This other part is we create a special time called Jan's in run, where if you terminate the simulation early, we jump, or if somebody's trying to do that, they give a time of their local virtual time of a negative value here. And so then essentially we can determine, well, if you're equal to that negative value time, let's go ahead and exit, and that will cause the termination of the entire system. We also say, of course, if we're greater than n time into the simulation, go ahead and return null. So then how this sort of works is we grab our the message out of the priority queue. If there isn't one, we continue through this and keep on going until there is one. So this prevents folks who have nothing to do from not being in GVT. We just leave them in the GVT algorithm, and they'll just keep trying to compute a GVT, because it usually means if there's no work they have, probably you're coming close to the end of your simulation. Again, if the arrival time of your message was greater than your look ahead plus GVT, then it means you've run out of events to process that are beyond the window. So let's go ahead and force a GVT calculation here by resetting the batch parameter. Otherwise, we're allowed to return null, and that will actually be the event that gets processed by the system going forward. All right. So in terms of porting Jans, it was sort of a strange path for us in terms of we could not run the /configure normally as you would do to build it. Instead, we actually would start it on a Linux machine to get it past the configure to get all the makefile set up. Then we would take the entire repository and move it over to our BlueGene, largely because the BlueGene doesn't have a full X Windows library or anything like that. It certainly doesn't have, in many cases, ours didn't have Flex Bison, XML, SQLite3, or zlib. So we ended up building all of those on the BlueGene. We turned off any need for TickleTK, and then we went in and edited by hand the actual compiler flags and the notion of which compiler is going to be using. In particular, these are for the XLC compiler. You can only get up to -03. If you try to go higher than that, you break the compiler. The compiler just will go for about 2 hours and then yield a wonderful seg fault. You also have to specify a large position-independent code piece. Otherwise, it runs out of, I think, the global symbol heap space. So you get an error there. But other than that, everything works very well. It links fine. And so we did this, and then we unfortunately discovered that when we started going at scale, there's a part of this where it's partitioning your model up, and it goes through all the gates, and essentially it's packing up and sending all the gates to every other rank, right? And so we were seeing that this wasn't working. It actually failed on the BlueGene. It was exhausting memory. Again, we only had 16 gigabytes per node. On clusters, you could do 5. So we'll actually talk a little bit about what's going on there. So the actual function we were working with is this one. This is connect remote gates and the partitioning of your parallel simulation. So again, it was essentially trying to re-emulate the broadcast, right? So try to do a point-to-point broadcast to all the ranks of the Seagate objects. Essentially on the BlueGene system, it would exhaust memory. On clusters, you could probably get away with this because they tend to have maybe a lot more memory per node. So it would sort of require too much memory. So we ended up rewriting the function to actually use, again, the collective operations on BlueGene Q, a broadcast, and we would iterate through each rank, where each rank would broadcast out its set of gate objects that it had within your model. Everybody would then receive that and process it on their side. So essentially you're matching up, hey, I'm modeling this part of the system. What part of the system are you connected to? And so you're doing this big exchange of that information. The other fix we did is we actually used the gate index and not a name to look it up. And we saw that there was a substantial performance improvement of about 6x for that. And so then at 2K MPI ranks, we discovered that this takes about 30 minutes to init a model with 64K nodes in it. This was pretty reasonable because such a model of this size would have normally taken days or possibly maybe even a week or so to run. So a 30-minute init time was actually pretty reasonable. In fact, it's pretty close to how long I think even the serial would take under certain conditions. All right. So in terms of our model configuration, we were working with a 64K fat tree. So this is the one model we were working with at the time. There are a bunch of others that they're working with as part of Design Forward, but due to confidential information, we're not really allowed to talk about those other topologies at this time. But this is really the largest network that we would actually be working with for our project. And so this just sort of gives you some of the configurations of it. Again, the simulation time for this was actually very short, around 120 microseconds. I mentioned the switches in this network model because the switches turned out to drive the amount of parallelism in the model, right? We couldn't break up a switch and spread it across processors. So we only had about 5,000 switches. So roughly speaking, you really only have, to divide this up evenly and partition it well, you only could probably run this on about 1,000 cores, which is exactly what we did. And so we compare that with a serial platform that's pretty reasonable. It's an AMD processor running at 2+ gigahertz, but it had a lot of RAM. It was one of our big servers. All right. So the first part of this is we wanted to measure or some validation, I should say, of the parallel versus the serial. And so we looked at the output statistics of the AMD runs for this configuration, and we compared that with both null message protocol and YANS. As you can see from all of the numbers, they agree fairly consistently across total packets processed. There's just very small variations, less than 1 or 2%. Across this. And really the difference is in determination of the simulations is where it's sort of at the end of where the serial, I believe, differs from both null message and YANS. So overall, we saw very good agreement with the parallel, and this is running on 128 nodes, 8 cores per MPI rank. So we saw a very good agreement between the two. So we felt good that there was nothing inherently wrong with the simulation.
Chris should probably point out that getting to that point was actually one of the major parts.
Yes, yeah, getting to this point was it was no easy matter. Part of it was actually, I think, getting obviously net file agreement and getting the output statistics to come through and things like that. But yeah, so this probably took longer definitely than the parallel part. So in terms of runtime, so I'll show across the different workloads. And so what we're showing is we made the number of cores equal. So we stayed at 1024 cores, right? But I'm showing this is the null message protocol here, and this is YANS. And so we're seeing a substantial performance improvement running in less than 1,000 seconds versus over like 4,200 seconds or so for null message. And this is at a 25% workload for the 64K fat tree simulation. So again, a substantial performance improvement here. What was also interesting is, so again, I'm using a certain number of cores, 1K cores, but I can change the number of nodes I'm running on. We saw a performance improvement as I went to more nodes. Part of this, again, I mentioned earlier, the L3 cache. As you gain more nodes, you get more cache. So there's some small benefit there for doing this, but again, we're probably using a lot more hardware than we really need to at this point. So this is actually how much of that time, so of that 4,200 seconds, roughly 720 or so seconds is spent in MPI for YANS. This is all of the null message. So they are piggybacking, but there's probably other messages as well, null messages happening here, because we're only at a 25% workload. Again, YANS is driven just by the strict synchronization, so it's actually relatively low. Right around probably 100 seconds of its total runtime is spent in MPI doing that. And so then we did a 50%, but I'm not going to show those results. They're sort of similar to the 80. So at the 80% workload, running around 5,000 seconds for YANS. Here it's only around 2,000 seconds. Again, the same story. We see a slight improvement for both as we increase nodes. Again, we're gaining some benefit due to local processing and gaining an L3 cache or L2 cache. But again, a nice substantial improvement. Not as much though, because essentially 80% workload, null message protocol is piggybacking those null messages on more of the real positive events going forward. And so this is the same graph. This is the MPI time. We spent roughly probably almost 20% of Jan's time is spent doing MPI stuff. Probably a little less for for Jan's, but again a similar story in terms of the overall time. And then finally, what was our speed up? Again, originally the motivation for the work was we wanted to see this order 50 to 100x speed up, and that was not comparing Blue Gene speed up, but to a reasonably modern server, the AMD server, and we felt we sort of met that goal in the sense of if we ran this, it took at 80% workload, 119,000 seconds or 33 hours, so a lot more time than your average coffee break, versus on Jan's we were seeing around half an hour or so, little worse. So this is very reasonable. So we saw speedups close to 64 times. So this is really where we wanted to be. So we felt we'd somewhat achieved the goal of our overall project here. So this leads me to future work. One is, we've still got to work out how Jan's terminates when you're in exceptions. In particular, there's one case that Cyril and the Venus team are very interested in confidence intervals. And if the simulation achieves its confidence interval, it might not have reached the end of the simulation time, you want to quit. So this is sort of still a work in progress in how to work with exceptions and get every MPI rank to participate in that last GVT to make that work. We would also like to modify, because the Blue Gene queue loves it when you use non-blocking MPI operations. It sort of doesn't like it when you use the blocking style ones. It's just sort of been the case with the way the protocol stack, the way MPI is implemented, and the lower level PAMI messaging interface is implemented. It just loves it when you use non-blocking messages. And so we would like to probably replace the blocking style with non-blocking. Another piece is we need to become more flexible. The Blue Gene likes you using these sort of powers of two core configurations, right? 1024 processors, 2048, 496, etc. And it's really hard to get 13824 node network to map well to that. And so you end up you'd like to do a partition of it, but have some idle ranks hanging out there. And so we want to be able to ensure that we can do that. And finally, we want to conduct a full performance study across all of these things, and we're working toward that. And ultimately, we want to roll this into the OMNeT distribution itself and make it open source so the community obviously can take advantage of it. And with that, I'm done. And thank you so much for listening to me, and I hope you found this somewhat interesting.
Thanks very much, Chris, for that very interesting talk. We have time for a couple of questions. Crystal clear. Yeah, I have the numbers that you showed there. Is that for the pure the running section?
This is just the running section, so it doesn't have it doesn't have the initialization time. Although it was interesting, I found that the serial initialization time was, because of the size of the network, was on par with what I didn't actually measure it, for real, but just sort of watching them run, they look to be about the same. So the init times between parallel and serial look to be very similar at this point.
I think we saw a fantastic achievement.
Thank you.
And well, actually, I remember that back at the time when I implemented parallel simulation for OMNeT, the null message protocol, I was wondering whether it's worth making it object-oriented and extendable and so on, because at that time I didn't see much opportunity to improve on the null message protocol using conservative simulation. We didn't want to go into implementing optimistic because it's C++ wise, it's hard.
Oh yeah, optimistic is we say there's no free lunch here, right? You either figure out the look ahead for your model, or you can go optimistic, but optimistic has its own minefield, as one would say, and so it's sort of you have to do a cost-benefit analysis. In this case, it was clearly because of the large amount of modeling infrastructure that was already there, rewriting that for optimistic wasn't even part of the conversation. So going conservative was clearly it. But having the optimistic, I think, framework that you put in place made this, I think, surprisingly a lot easier than we would have originally thought when we just used once we figured out how to use your routines there. So it worked out pretty well.
Okay, and I think the message to bring home from the presentation is that probably the essence is that you took it was the way it was possible to get rid of the null messages, and that you exploited the special hardware that could do map reduce very efficiently.
Mm-hmm.
Right?
Absolutely, yeah, to do the reduction operation, absolutely. And the good news piece is it's not that reduction hardware exists not only in blue gene queues, but exists in more common clusters if you buy an InfiniBand network. Mm-hmm. So they're starting to put that type of capability, or definitely the lower latency in InfiniBand networks. So if you have a small cluster with InfiniBand, you can probably see very similar performance gains.
I should point out that this runs perfectly fine on bog standard Linux installations.
Oh, yeah.
So here locally, actually, I'm also using it not with 1000-way parallelism, but maybe 4 or 8-way parallelism, basically taking advantage of the multiple cores that every processor has nowadays. And you get speed up, not quite as good as what he's showing on BGQ, because the dedicated reduction hardware is missing, but you get speed up. And if that means, if I run 4 MPI ranks, it means that instead of 2 weeks I have to wait maybe 3-4 days, then that is quite a significant gain. So I think everybody in this room who has large models to run could benefit from this without having to buy a BGQ. If you want to buy a BGQ, friendly local IBM representative.
Or write a proposal to Ulick or to us, and we can get you.
Yes. Actually, a lot of those systems are actually open to communities. Just you have to write a proposal what you want to use it for. Yeah. Okay. If there are no further questions, then we can proceed to the first coffee break. So everything should be arranged right there, and then we'll reconvene at 10:20. I would ask the presenter of the next session to talk to Michael over there to get set up. Thanks, Chris.
Thank you.